Awesome. Wonderful. All right. Thanks again. It's a pleasure to be here. As Chen mentioned, the talk is on various aspects of federated learning, in particular, how to make it social, secure, scalable, and efficient. Different parts of this talk are joined with a lot of collaborators that I have listed and acknowledged them here. So it's a list of a group of collaborators that we have been working on this topic for some time. So as Chen mentioned, I'm also, running the FedML company, which provides deployable federated machine learning. So in this talk, I try to mostly focus on the research aspect of federated learning. Maybe towards the end, give a little bit, introduction in how you would be able to deploy that in real world if you are interested to run federated learning in your platform, in your environment through FedML. All right, so given that there has been several talks beforehand, I think all of us are motivated on federated learning. Makes my job much easier. There is a lot of data being born at the edge of the network, and this data is often very private. For example, the data that you have on your cell phone, your messages, your images, your text, the data that is collected by IoT devices, like Alexa devices, AI-enabled devices, healthcare IoT devices, as well as the data that different silos have. For example, the data at different hospitals, banks, department stores, a lot of data. The main goal of federated learning is to enable collaborative learning at the edge of the network without the need to move any data or sharing any data. So it's kind of learning without sharing. And it's gaining a lot of attention because it addresses several challenges that we are seeing in the world today. For example, because of rise of privacy, regulations, liability, there is less possibility of sharing the data and moving the data between the silos. From the scale of the growth of data that is generated at the edge. For example, on this plot, the green, you see the amount of human-generated data. The blue, you see sensor-generated data. Compared with business data, you're seeing that it is really becoming much more. So from a scalability, performance perspective, you rather do your machine learning and training of the machine learning models at the edge of the network without bringing it to the cloud. Also, from performance perspective, by doing learning at the edge, it is possible to much better personalize the trained models. For example, training a computer vision model that matches the characteristics of a person, or a speech recognition model that matches the accent, etc. So that's why from the performance perspective, it is also very much desirable to do the training at the edge, not just because of the security and privacy. Finally, because of the excitement of Web3 and Edge AI, there is more and more demand for empowering data owners, AI developers, and by monetizing and enabling decentralized learning at the edge. This is very much along with the concept of Web3 and the content being owned by the people who have it. So that's why federated learning is gaining a lot of attention in various verticals, from healthcare to finance to retail, a smart city, a smart home, IoT manufacturing, autonomous driving, and virtual reality, metaverse. Again, all of these correspond to the scenario. A lot of data at the edge. You need personalized high-performance models to be developed for each user, and federated learning can be a very promising approach to these problems. So how would it work? I'm sure most of you are familiar with the concept of federated learning. At a high level is simple. It has two main components. In the first part, you train locally at each device or each silo based on the data that is locally available. Then in the second phase, you try to aggregate that trained models together to come up with a better global representation. And you continue doing that at several rounds until the model converges. Typically in federated learning, there are two settings that people would refer. On the left here, you see cross-device federated learning. That's the setting of learning across many edge users like phones, IoT devices. The other scenario is cross-silo federated learning. This is the scenario of learning across data silos, like hospitals, banks, factories, department stores, etc. Nevertheless, at a high level for running federated learning, what each silo or user would be doing in the first step uses whatever it has locally, train a model. Then the server would do the global aggregation because each model by itself is low quality. So you have to combine them together to come up with a better representation of the model and the data. So while at a high level, it is simple, while you try to use it in practice, it is actually a very challenging problem. And there are several reasons for that. Here I have categorized three set of challenges in federated learning. One of them is from the algorithm design perspective. For example, as you can see, model aggregation in federated learning is a very important component. A naive way is just weighted model averaging. That's called federated averaging. But there has been a lot of effort to improve that, in particular, make it suitable for heterogeneous settings. And several talks beforehand talked about different ways of improving aggregation. For example, the questions on when to aggregate, what to aggregate, and how to aggregate the models are very important problems that have been studied a lot. Another aspect is in federated learning, you have heterogeneity of the data. You need to personalize the models for the users, and you need to make sure that you are fair in a sense that every user or every silo gets a chance to contribute. Also, from algorithm design perspective, one of the issues that rarely people talk about is lack of labels at the users. While the users have the data, typically that data is not annotated, not labeled. So it is very important to think about learning approaches at the edge that deal with no or weak labels. One level above, you can think about the scalability and system design. For example, how to deal with resource constraint, edge nodes, how to train large models over edge nodes that maybe have one GPU or even don't have GPUs. Thinking about how to scale it from a domain of distributed learning, which is at most like hundreds or thousands of GPUs, to a domain of learning at the edge with potentially millions of users. And also, as we think about these larger scale systems, there is going to be stragglers, heterogeneity of the resources. So how to deal with these are very important problems. Another layer higher, from algorithm to system to users, a key component of federated learning is thinking about the trustworthiness aspect of it. For example, how would you design model aggregators that are robust, resilient? How to actually guarantee security and privacy for the users? Or how do you tolerate adversarial users? These things become important as you democratize learning at the edge. Okay, so that's why, while a high-level FL is easy, if you want to do it in practice, it is actually very challenging. And there has been a lot of research from the community in the past couple of years. For example, last year around, there were a lot of publications trying to think about some of these challenges. And I think right now, the technology is mature in the sense that we are seeing some of these algorithms performing well in the practice, and there are deployable systems that I want to talk about today. So my plan for the rest of this talk is maybe highlight some of the key questions that I think they have been less explored in the community, and talk about potential approaches for them. For example, one question is, would you be able to provide formal security and privacy guarantees for federated learning? Keeping the data where it is, that's a very good step, but it's not a formal guarantee. So what can we tell about federated learning? Another part is, if you want to run federated learning over resource-constrained edge nodes, like your phones, or maybe servers with 1 or 2 GPUs, can you really do that? Typically, when people talk about federated learning, it is assumed that everybody can locally train a model. But often, in reality, it is not true, especially for larger scale vision models. You cannot do that. Another set of questions is, how would you run federated learning without having labels and annotations at the edge? And finally, would you be able to scale it to millions of users? Okay, so I think these are 4 important questions that are needed to be studied in order to make it, make federated learning deployable and used at a, broader scale. Okay, so that's the plan. I highlight some research directions along these questions. And then after that, I will talk about some deployment of federated learning if you want to use that today. So let's start with the security and privacy guarantees of federated learning. So as we mentioned, in vanilla federated learning, the privacy of the users is ensured by avoiding data movement from users. What it would mean is that during federated learning, your images, your data, or a factory's images, they all stay at the server in that facility or that user. That's very good. But as we all know, since the locally trained models are moved back to the server, it is possible to invert the models and apply model inversion attack. And you're very familiar with various model inversion attacks. For example, here is one that you are reconstructing a model, an image that was used in the training by inverting the trained model. So that's why one layer above is in federated learning, we typically rely on secure model aggregation. And what secure model aggregation would mean is that we want a mechanism to guarantee that the server will not even learn the locally trained model of the silos or the edge users. Okay, so the only thing that during federated learning is learned is the global aggregated model across many users. Okay, so that's why secure model aggregation has been actively pursued in federated learning. You can think about it as a multi-round secure multi-party computing problem in which the goal is to just learn the aggregate model, but not the individual model. One challenge in federated learning that makes it different from the typical conventional multi-party computing is that you also have user dropouts in the system. Nevertheless, there has been a lot of work on how to make secure model aggregation efficient and scalable. There is a variety of work here. For example, from our group, there is a new protocol called LightSecAg that is very efficient, and you can also apply it in the case of asynchronous federated learning, our upcoming paper at MLCs. There are also other approaches based on leveraging differential privacy, homomorphic encryption to make it easier for deployment, and also leveraging some hardware security. But nevertheless, what I want to tell you is that even if you apply secure model aggregation, meaning that the server only learns the aggregate model, still with all existing protocols, if you are not careful about how you are aggregating across the users, there is potential for serious privacy leakage across multiple rounds of federated learning. You may be surprised. So let me show you maybe a cartoon to show why this type of leakage happens. This is typically happening because of the partial user participation, meaning that at all rounds, not all the users would participate. This is true in the cross-silo as well as cross-device. For example, let's say in one round of federated learning, users 1, 2, 3 participate. By secure model aggregation, the server only learns the aggregate model across the 3. In the second round, users 1 and 2 only participate. User 3 is maybe taking a phone call, not connected. So the server again applies secure model aggregation and only learns the aggregate model of user 1 and 2. Now what you can see is by combining these two linear combinations, the server, if it subtracts them, can very well approximate the model of user 3. Okay, and after that can try to invert it and learn the data set of user 3. Okay, so this is a cartoon demonstrating what can happen. This issue is actually very serious. We have demonstrated this attack in a real-world deployment. For example, let's say you have 40 users with random selection, and what you are applying is you apply secure model aggregation, so no leakage at each particular round. But then you try to apply linear estimator at the server to combine the local models to estimate the individual model of the users. On this histogram, what I'm showing is that the histogram of the reconstruction error. Okay, so x-axis is the reconstruction error for individual model of the users by the server. The y-axis, the frequency. And this is normalized error. So what you can see is that for many users, the server is able to learn their local models with a normalized error of less than 0.005. It's like, think about the signal to noise ratio. It's very high. So the server is essentially learning the individual model of many users, and for all users is even below 0.025. Then after that, you apply model inversion attack, and here is what we have shown. For example, you can then reconstruct one of the images that was used in the training. Okay, so this is a serious issue. What can you do? The way to formulate this problem is thinking about these equations. You want to put a structure on these equations to guarantee that there is no way to combine them to come up with an equation which is sparse. Okay, so it becomes putting a structure on user selection to guarantee that the resulting equations that can be combined will not result in a sparse equation like this one that leaks the model of one user. And that's the scheme that we have, multi-round secure aggregation. The details, you can take a look at the paper here. I'm not going to go to the detail, but in the same setting as before, you can see that once you apply multi-round seg-ag, now the reconstruction error for all the users is becoming larger than like an order one constant, 0.25. Again, this is a normalized error, so SNR being order one means the noise is proportional to the signal, and you can't really reconstruct anything. Even visually, you can try to apply the same inversion attack on the estimated noisy model. On the very right side, you can see that now there is really not much that is reconstructed from the original images. So visually, you can see the privacy that you can give to the users by applying secure aggregation each round and multi-round client selection in a structured manner. So that's very good. But maybe we want to go even one step further and say beyond visual and being robustness to various attacks, can we prove theorems and show that federated learning by applying secure aggregation at each round and multi-round secure aggregation is giving us privacy guarantees? Okay, so we have done that. It is possible to do it. Maybe I give you some intuition behind that. Thinking about, given that you are guaranteeing that you are only learning the aggregate model across a large cohort of users, then by central limit theorem, you can show that the model of the other users act as a Gaussian noise to mask your own model. And then you can try to bound the leakage in terms of mutual information that is leaked from the aggregate learned model about the individual model of the users. So that's the results that we have. What we can show is that now the mutual information in terms of the leakage decreases as 1 over the number of users. So it's kind of the more users join a federated learning system, they protect each other more and more. This is similar to like blockchain systems. The more users join, the security becomes larger. Here, the more users join, the privacy gets better because others behave as a mask for protecting each other. What you can show here, for example, for training various models like a small linear model or CNN models, on this plot, on the x-axis, we have number of users. On the y-axis, we have the average leakage about the data of the users from the entire federated learning process. Okay, so this is divided by the number of users, so it's the average leakage. What you can see is that for all the models, we have 1 over the number of users leakage. So it's kind of, and the good news is that as you have, about 10, 20 users, the leakage is already becoming very small. So you can think about for your setting, how much leakage you can tolerate, and then, try to pick the batch sizes and the number of users to match the leakage you want. If you can increase the number of users, there are other ways that you can do. For example, the leakage you can also show decreases with the batch size. So maybe if you can afford to increase the batch sizes, the leakage would increase. So these are the good news in terms of formal guarantees that you can give for federated learning. Very good. Let me move on to the second part, which is now that we have some security privacy guarantees for FL, can we really run it across resource-constrained edge nodes? Okay, so as we all know, in reality, if you want to look at the edge nodes, you have limited memory, you have limited computations, you have limited bandwidth, and vanilla federated learning assumes that every user can train a large model locally. But what if you can't do that? Okay, so you're going to run out of memory, compute, or it's going to take a very long time if you want to do it, for example, across an Android device. So here is one approach that we have been thinking about for tackling this issue. At a high level, maybe instead of thinking about federated learning as averaging of the locally trained models, maybe we should think about going beyond model averaging. And one way of doing that is to think about federated learning as a knowledge transfer from many small edge nodes to a large model that you are training over the cloud. Okay. So the question here is that, or high level idea here is that, could we formulate federated learning as a knowledge transfer from compact models at the edge to a large model at the server? And this way, the problem can be viewed as a federated knowledge transfer. So that's a method that we have been developing called FedGKT. It's called Federated Group Knowledge Transfer. And at a high level, here is how you can visualize FedGKT. The idea is that, let's say, you can only afford to train a compact CNN at each edge node. Now, what this CNN would be doing is going to have a feature extractor and a classifier. Okay, so what you want to do is to transfer the knowledge of the extractor to the server so that the server can train a very good large scale classifier. So how can you do that? You can do it as a forward knowledge transfer from these students to the teacher via a knowledge distillation loss. So what would it mean? You're going to send the intermediate features that are extracted to the server along with the soft labels. So the server classifier tries to come up with soft labels that make it as close as to the soft labels that were generated by the feature extractor at the edge nodes. So this way, all the edge nodes are helping the server to come up with a very good larger scale classifier. But if you only do that, the issue is that the knowledge transfer is only one way, and the classifier at the edge nodes, these are small classifiers, become very primitive and won't improve. So what it would mean is that the feature extractors won't keep improving across several rounds. So in order to overcome this challenge, you also need to have a transfer back mechanism in which you also apply a knowledge distillation loss between the soft labels that are generated by the edge nodes, as well as the one that are generated by the good classifier of the server, so that they push the feature extractor and classifier, the compact feature extractor and classifier of the edge nodes to also improve. This way now you can think about it, you have a closed loop in which the edge nodes are helping the server to train a large classifier. The server is helping the edge nodes to also improve their feature extractors. Once you do that, mathematically you can write that as an alternating minimization problem that does exactly what I mentioned to you: edge nodes helping the server, and in the reverse, server helping the edge node. And this mechanism keeps improving as you run FedGKT across several routes. Now let me show you what is the benefit and what can you get with this approach. Okay, so let's look at a setting. Let's say you want to train a large model. Actually, I should change that to ResNet 110 across all the edge nodes. And let's say as a baseline in vanilla federated learning, you are going to train that large model, ResNet 110, across all the edge nodes, which in reality you cannot afford. It's going to take a long time. Now, in comparison, let's say you apply FedGKT by training a very tiny model, ResNet 8, at each of the edge nodes, while they collaborate for training the large model at the server only, ResNet 110. Okay, so these 56, just ignore it, make it 110. Okay, so these are the two, like a baseline, just applying federated averaging, assume you can train, there is no resource constraint at the edge. FedGKT, you have a very tiny model at the edge. As you can see, as you go from ResNet 110 to ResNet 8, you get about significant saving on the amount of flops you need, on the number of parameters. Like you get about 2 orders of magnitude saving on compute, memory, as well as resources that you would need. So huge saving. The question is, what is the drawback? Okay, so here is the comparison. We have looked at the comparison in various computer vision benchmarks, CVPR 10, CVPR 100, CNIC 10. Let's look at the ResNet 110 that I mentioned. The baseline is federated averaging. This is the case that assuming that you have no resource constraint, like the best that you can hope for, but now having 2 orders of magnitude less compute at the edge. What you can see is there is like little to no drop in the accuracy. Okay, so surprisingly, you don't lose anything by thinking about the problem as a knowledge transfer from the edge nodes to the server. Okay, so you are matching the performance as if you are training the large model everywhere. So what it shows is that we have shown the promise of this in CNN type models. There have been some follow-up works to apply that for bear type models. Okay, so the same structure and intuition can be applied there. I think it's a very promising approach to generate thinking about maybe more broadly as trying to do partial training at each of the edge nodes. Sometimes this partial training can be like a compact CNN that you do the knowledge transfer. Sometimes the partial training may be in the form of training part of the model at the edge nodes. So I find these approaches to be very promising in practice. All right, let me move on. Maybe I can go a little bit rapidly on the two other components. The third aspect of the talk was scalability and system design in federated learning. And the idea is, you want to know, now we have privacy guarantees, we can run it across small edge nodes like mobile phones, but now we want to scale it and run it across millions of devices. So what are the challenges? What are the potential solutions to that? Okay, so how would we scale it? The first thing you would notice is that if you apply synchronous federated learning, meaning that at each round, trying to wait for a fixed cohort or a large cohort to finish their training, these approaches won't be scalable because as you are increasing and you're opening up to a large set of users, you are doomed to have stragglers, failures that is gonna take the federated learning to be very long. Okay, so it's very difficult to think about synchronous FL in a very large scale deployment. That's why there has been interest in the community to think about asynchronous aggregation. For example, a recent one is FedBuff and Papaya by the Meta team that they have proposed buffered asynchronous federated learning. And the idea here is that in these approaches, you try to define a buffer and say at any time that a user finishes the training, right, you keep waiting till a certain number of users have finished, they contribute to the buffer. For example, in this figure, maybe my buffer size is 2. Once device A and C finish, my buffer is full. I aggregate the model, giving back to the other ones. But for example, device B that never finished, it doesn't terminate the work. It continue updating the model that it has been working on and ignoring the recent update. Why? Because maybe this user can contribute in a future round. Okay, so if at each round you make it synchronous, and once there is a buffer full, you send the aggregate model to everybody and they terminate, they work on updating based on the new weights, then a slow device will always be a slow and will never be able to contribute. This way, by making it, allowing some slackness and allowing for stale models in the system, then device B is able to contribute at a future time with a stale model. So this way is going to be accounted and it can contribute. But the challenge of it is that, we have been trying to look at how, these buffered asynchronous approaches would work. The challenge of it is that there is unbalanced participation among clients, meaning that still fast clients will contribute a lot. And there is going to be a lot of users will get little chance of contributing. Or maybe they contribute, but they contribute with very stale models. Okay, and what we have seen is that, for example, comparing with synchronous federated learning, schemes that are buffered like FedBuff, they can create huge drops on the accuracy. For example, this is for CFAR10. Let's say you are training a ResNet 20, we see significant drop. And as I mentioned, this drop is caused by still some weak clients not be able to participate often, and also they participate with the stale models. So the question is, how can we overcome that? That's where we have a new scheme, Timely FL, that we try to leverage partial training at each user. So what it would mean is that if you have weaker clients, let's help them to speed up their training. How can we help them? Asking them to focus only on the last few layers and only do the backpropagation and model update on those last few layers as opposed to all the layers. So this way, still they can speed up and try to participate more often. Okay, so what we have seen is that in the same setting that I show you to you, using these approaches, first of all, it is possible to increase participation rate by the users a lot. So you can see that here, a lot of users get to participate more. So it's becoming more fair. It's becoming also, staleness is going to be reduced. You combine both of them together, we see that, the performance can improve a lot. Okay, so at the same time, it is important to make it asynchronous, but also you want to create more opportunities for weak clients to participate via partial averaging. I think that's a promising approach to deal with this problem. All right, so let me skip through these parts and mention a little bit about the final challenge that I wanted to talk about, which is lack of labels and self-supervision at the edge. I think this is another critical component of federated learning, often ignored. You have lots of data at the edge, but nobody is going to label them for you. So how are you going to be able to match centralized learning over the cloud, where you can use various, maybe volunteers or resources for labeling the images? Okay, so one approach that we have found promising, actually, I'm going to talk about two of them. One approach is through using user feedback. Okay, so the idea is that one opportunity at the edge is that it is true that the users are not going to help with annotation, but they're going to be the users of the trained model. Okay, once they're using that, that sometimes implicitly provides feedback to you. And sometimes maybe you can ask them for feedback. Okay, so I think these approaches are very promising. Let me mention type of user feedback. For example, a screen-based feedback is going to be, very important. For instance, we have looked at the scenario of training a computer vision model for figuring out the angle that the user is looking at the camera, like angle of gaze. In those settings, one way that you can leverage the user feedback is based on where the user is clicking. If it is a virtual reality, they're going to, click on the screen, or maybe shoot at a place at the screen. This will provide samples through that feedback on where they actually meant to look at. Okay, there are other ways, users, work with a screen. Maybe they touch different parts, so you can collect a lot of screen-based feedback. It is also, possible to get through, the way that the users use the result of the inference to get the feedback. For instance, let's say in a maybe AI-assisted bot setting. Let's say you are talking to your Alexa device. A type of positive feedback would be the user is asking Alexa to play a song, and then Alexa starts playing the correct song, and the user keeps listening for a couple of minutes. So given the fact that the user listened for a couple of minutes is a good indication that the predicted label was indeed correct. It can also be through negative feedback, meaning that the user says, play this song, Alexa will play the wrong song. User will respond back by saying, Alexa, stop playing. So you can say, this is a high probability corresponds to the case that the predicted label was wrong. Okay, so through that interaction, you are getting label information. Of course, you should be aware that these are also going to be noisy. For example, maybe the user asks for a song, Alexa plays the wrong song, but the user changes their mind, or vice versa. Okay, so these are not 100%. So in order to leverage them, of course, they generate labels, but there is going to be noisy. So to leverage that, you have to leverage noisy user feedback. We have been looking at these cases, for example, in the context of NLP tasks, for example, text classification across various data sets, like 20 categories, 2 categories. And you can model user feedback by probabilistic way to account for noisy user feedback, gamma representing the fact that the positive feedback is correct, delta representing the case that the negative feedback is correct. All right, so what you can do here is if you want to leverage positive user feedback, that's very easy to leverage that. Since it is positive, you can just pretend that the labels that you have predicted are correct. So you have non-labeled data, and you can use that in your training. So what can you get? For example, in the benchmarks that I mentioned to you, you can look at the setting that there is initial model. You just apply self-supervision. You provide positive feedback but noisy. We set the parameters according to some empirical studies that we did, as well as positive feedback, no noise. So what you can see is that compared with self-supervision only, positive feedback provides huge improvement, right? So it's getting you very close to the full supervision. So it's showing a very promising technique for label generation. Of course, if it is noisy, still there is a gap. That's where you have to think about robust learning algorithms that are noise robust. Okay, so to bridge that gap. For using negative user feedback is more challenging because, as I mentioned, in positive user feedback, you can just treat the predicted label as a true label. In the negative user feedback, the label is not the one that you thought. So the question is, what label would you use? So in that case, there are various methods. For example, you can use one method in learning with biased complementary data, complementary labels. And the idea is that you try to use a confusion matrix to try to figure out what labels, if the label is not one, what are the possible labels for this sample? Okay, so try to assign it smartly as opposed to saying that all other labels are equally likely, where that won't be a good way of leveraging the labels. So now if you apply that, meaning that now you leverage noisy user feedback, negative user feedback based on what I said, and you apply all the feedback, so you can see negative user feedback is also providing huge improvement and getting us very close to full supervision. So in general, as I mentioned, I think the idea, these are very recent results that we have, the idea of leveraging user feedback to account for lack of labels. I find that promising. Of course, it is context specific, not always is possible, but in a lot of settings, it is possible to do. Of course, you can also think about self-supervision and just try to do self-supervised federated learning. There is going to be a lot of challenges for doing that. Unfortunately, I won't have time to talk to you about that. Maybe I refer you to our paper here if you are interested on running, federated learning in a fully self-supervised manner. So instead, maybe in the remaining 2 or 3 minutes, I mentioned to you a little bit about, we talked about a lot of algorithm, a lot of advances in the field by us and other, collaborators from the community. What if you want to use that in real world? What can you do? That's where we have started FedML that gives you full deployment. In general, FedML is an open source platform used widely in the community. A lot of members, a lot of industrial collaborators use that. But beyond the open source part, what we have been doing recently is producing an Edge SDK that enables execution of federated learning across any setting, whether you want to run it across servers that have GPUs and CPUs, whether you want to run it across Android devices like phones or any Android IoT device, or even a smaller like microcontrollers for training a smaller models. Okay, so this Edge SDK is container-based, you can run it anywhere. And also we have an MLOps platform that makes it zero code, user-friendly, so that in a zero code manner, you can just focus on designing the application, designing the algorithm, and deploying it across any edge settings. Okay, so together with FedML, we provide 2 solutions. One of them is Octopus setting for training federated learning across silos, across silo federated learning. Another one is FedML Beehive that is tailored for training across larger scale edge nodes, for example, mobile or IoT devices. So what I had a 3-minute demo to show you how you can use FedML. But let me pause here. Maybe I ask Chen how much time I have before I start that video.
Yeah, go ahead. So you have like 5 or 6 minutes still.
All right, so let me start, play that video, and then that would be the end of the talk. If you want to use that, how you can use FedML.
Hi, welcome to FedML. Today, I will walk you through our versatile and user-friendly MLOps, which provides the federated learning service and Edge AI SDK for developers or companies to do open collaboration from anywhere at any scale in a secure manner. Essentially, our MLOps can seamlessly migrate your local development to the real-world edge cloud deployment without code change. We have different platforms for different training scenarios. Octopus works cross-silo federated learning, while Beehive works for cross-device federated learning. Users can write once in local developing environment and run the training anywhere. Let's take Octopus as an example. There are 4 key steps. First, you only need to write the source code once, which is to develop the source code and generate deployable packages locally. And then you can create an AI application and upload the packages on Octopus. Second, you only need to type FedML login, command line to bind FedML agent to the edge devices. Third, you can start to invite collaborators, create a group and a project with user-friendly UI. Finally, you will be ready to run it everywhere by starting the training and experiment tracking. Let's get started. We will use the one-line example in FedML GitHub as an example. First of all, you can make changes in source code and configurations, such as fedml config.yaml file. By running fedml build, command line with different arguments, you will generate your server package and client package. Now, you can visit open.fedml.ai, create an application, give it some tags in different dimensions, make an easy-to-follow description, upload the packages you just built, modify the hyperparameters again as needed, and then click Create Application. Second step is to bind the FedML client agent with a simple command line that is FedML login account ID. Once you see the successful information in logs, you can go to the Edge device page to check and modify the device name to make it easier for you to differentiate. The third step is to invite your collaborators and build a group for collaborative training. Click Invite Collaborator, copy the link, and send the link to your collaborators over email, Slack, etc. They can open the link and accept the invitation. Now you can see each other in My Collaborators and create a group. After that, you can create a project and start a run with the application you saved. Finally, our ML Ops platform provides experiment tracking for you, including the training progress and device status, the training results such as accuracy and loss, system performance such as fine-grained running time profiling, CPU and memory utilization, and training flow. That's it. We hope our ML Ops make your life easier. Welcome your feedback.
All right. So as I mentioned, using the FedML ML Ops is very easy to do. If you are interested in various application domains, we have libraries devoted to CV, NLP, data mining, and time series forecasting. For example, FedNLP has a lot of benchmarks that are ready and available for deployment. In natural language processing, in FedCV, we have a lot of computer vision benchmarks. And in FedGraphNN, a lot of data mining benchmarks. The same for time series forecasting in the FedIoT libraries. So not only you get the deployment, there is also a lot of applications that are already available. You can fine tune them and deploy that. All right, so let me conclude the talk. Hopefully, as we discussed, all of us agree if federated learning has the potential to provide a lot of benefits to the machine learning ecosystem. It's still a challenging problem. There are many challenges, open problems. So from research perspective, there is a lot of problems to work on. I also talk about FedML. It's a platform that you can use it for both research as well as real world deployment. So if you are interested, please join our open community and let's push the area forward together. Thank you.
Okay, all right. Thank you, Professor. All right. Okay, any questions? Okay, Professor, I have one question. So yeah, I think the FedML system is very good because it has different, say maybe the modules or libraries designed for different applications, right? Computer vision, natural language processing. And so in that case, I'm assuming all the like a benchmark, baselines will be there. So, the users can easily maybe, run some of the comparison. Is that right? For
That's
example,
correct.
vision problem like image classification, those kind of thing.
Exactly. So, for example, in FedCV, I mean, answering your question, there is, libraries for image classification, image segmentation, object detection, and this, is growing more, meaning that any user can contribute, bring more benchmarks. For example, in terms of the model, we have various, BERT type models. We have various like transformer type models. We have various CNN type models that are available, to use there.
Yeah, great. Yeah, I'm glad you mentioned the transfer model. So I think in the vision community is kind of gradually adapting to the vision transformer. So it's glad there's going to be some transformer model there so people can play with. Yeah.
Definitely.
Okay, great. Thank you again for the great presentation. And I think this is a great framework. We'll definitely check it out for the FedML. All right, thank you.
My pleasure.